Imagine two massive objects rushing toward each other at extraordinary speed. They are not cars or planes, but stars, black holes, or neutron stars. When they finally collide, the energy they release is not just large, it is beyond what most people can picture. The numbers are so high that our everyday comparisons struggle to keep up. Still, we can try. The most powerful nuclear weapon ever tested produced energy equal to about 50 megatons of TNT. That single blast could level a city. Now, take that amount of power and multiply it by billions. That is closer to the scale of energy a cosmic collision would release in an instant. A neutron star is one of the densest objects in the universe. It is the core left behind after a giant star explodes as a supernova. Just 1 teaspoon of neutron star matter weighs more than a mountain. Imagine 2 of these stars spiraling toward each other. Their gravity pulls them closer while they spin faster and faster. When they crash, the force rips them apart, sending shock waves through space. These shock waves, called gravitational waves, ripple through the fabric of space and time itself. We have detectors on Earth that can sense these ripples even though they arrive billions of years after the event and are faint by the time they reach us. The scale of such power is far beyond anything humans could create or even control. So picture the energy. Every second, the Sunday gives off more energy than all of humanity has ever used throughout history. Now imagine 2 suns colliding in a single violent instant. The energy from that clash would not last seconds, but would flash out in fractions of a second. Gamma rays, the most intense form of light, would burst outward. Matter would spray into space at nearly the speed of light. In some cases, the collision could even form a black hole. All of this happens in silence because sound cannot travel through space. Yet the violence is unmatched. If you compare it with human weapons, the contrast becomes even sharper. A hydrogen bomb is terrifying to us because it can wipe out entire regions. But if a neutron star collision were to happen within a few dozen light years of Earth, the energy burst could strip away our atmosphere or even destroy life here. Thankfully, these events usually occur in distant galaxies far from our planet. They are rare in human terms, but common in the lifetime of the universe. Astronomers watch for them not because they pose danger to us now, but because they offer a window into how elements are formed. Gold, platinum, and uranium, for example, are believed to come from the explosions caused by these cosmic crashes. The jewelry we wear and the fuel we use for nuclear power may trace their origins to unimaginable collisions in the distant past. Think about the ground shaking from a large earthquake. The energy it releases can topple buildings and reshape landscapes. Now, take that feeling and expand it beyond measure. A neutron star merger releases more energy than all the earthquakes, hurricanes, and volcanoes in Earth's history combined. And it does so in the blink of an eye. The numbers scientists use to describe these events often run into the millions, billions, or trillions of tons of TNT. At that point, the words almost lose meaning because the scale lies outside normal human experience. One way to make sense of it is by comparing distances. Suppose the explosion happened in a galaxy millions of light years away. Even from that vast distance, the flash of light could be bright enough to see with a telescope on Earth. That means the energy traveled across a mind-bending stretch of space and still carried enough power to register, if such a thing happened, within our own galaxy. The night sky would light up brighter than the full moon. Imagine stepping outside and seeing a new light in the sky, so intense it casts shadows. That glow would be the last breath of 2 stars colliding far away, their combined mass turning into raw energy. These events also create black holes, regions where gravity is so strong that nothing, not even light, can escape. The birth of a black hole is itself a release of energy. Matter falling into it produces jets that can extend for thousands of light years. Some of these jets travel so fast they almost match the speed of light. They plow through space, carrying energy across unimaginable distances. Entire galaxies can feel the effect of such an event. It is as if a single spark started a firestorm that spread through cosmic neighborhoods. The math behind these events is straightforward in one sense. Einstein's famous equation E equals mc Phi tells us that mass and energy are linked. If you convert even a small amount of mass into energy, the result is enormous. A single kilogram of matter, if converted completely, would yield about 90 trillion joules of energy. That is enough to power a large city for days. Now, consider that a neutron star has more mass than our Sunday. When even a fraction of that mass is turned into energy during a collision, the result dwarfs all human scales. To see it in more human terms, picture a match lighting a candle. The flame is tiny but visible. Now, picture every match ever struck in human history lit at once. Multiply that by billions, and you might get close to imagining the glow of two stars colliding. The burst is short, but the memory lasts. Light from collisions that happened billions of years ago still travels across space, carrying the story of their violence to us. When we talk about unimaginable energy, it is not because scientists cannot measure it. They can. It is because the human brain evolved to understand the scale of rivers, mountains, and storms. Not galaxies and exploding stars. Numbers that describe cosmic collisions stretch the limits of comprehension. They remind us of how small we are in the universe. Yet they also show that the same laws of physics that power a car engine or a light bulb also drive these massive events. The difference is only in scale. A neutron star merger is the same rulebook played out on the largest possible field. If you stood on a safe platform far away, watching such an event unfold, you would see nothing like it on Earth. A flash of high-energy light would sweep past you, followed by matter racing outward faster than bullets. Space itself would ripple. You would not hear it, but the universe around you would shiver. The power of the event would not just destroy, it would also create new elements would form. New stars might be seeded by the debris. The cycle of death and birth would continue, powered by energy too large to grasp. Imagine waking up one morning and everything around you vanishing in the blink of an eye. Not slowly, not over years, but in a flash so quick the human brain would not process it. The idea of an instant global catastrophe is not just about destruction on a local scale. It is about the Earth itself ceasing to exist in the form we know. When energy of a certain magnitude strikes, the crust, oceans, and atmosphere would not just burn or break apart. They would vaporize. That word means the solid and liquid matter making up the planet would turn directly into gas or plasma, leaving behind no familiar surface. This is the kind of outcome that happens if an object with enough energy hits Earth, or if a cosmic event unleashes its power close by. Start with the crust. The crust is the outer shell of the Earth, the part we live on and dig into when we mine or build. It seems thick and stable, but compared to the rest of the planet, it is thin. It makes up less than 1% of Earth's mass. Beneath it lie the mantle and core. But the crust is all that stands between us and the deep layers below. An energy strike strong enough to vaporize the crust would break apart mountains, cities, and even continents in fractions of a second. Think about a sheet of ice on a lake in spring. One strike of a hammer, and it splinters and shatters, breaking into mist if the blow is hard enough. Now scale that image to the size of a planet. The crust would not shatter into chunks. It would transform into vapor, a cloud of material blown outward into space. The oceans would follow the same fate. Water seems immense when we stand on a beach and look at the horizon. The Pacific Ocean stretches thousands of miles, and its depth reaches more than 6 miles in places. Yet when the energy is high enough, size and depth do not matter. Every drop would flash into steam, not the kind of steam that comes from a kettle, but superheated gas glowing with energy. Imagine the sound of a pot of water boiling, then multiply it to the scale of entire oceans turning into vapor at once. The force of that change would expand outward, creating a shock wave that carries part of the ocean into space. The seas that once supported life would vanish in an instant. The atmosphere would not escape. The air we breathe is a fragile layer, only a few dozen miles thick. We rely on it to shield us from radiation and to hold the conditions needed for life. In a global catastrophe of this scale, the atmosphere would not be burned away slowly. It would lift off the planet in a flash. Molecules of nitrogen, oxygen, and carbon dioxide would be torn apart or swept away into space. Think of a candle flame flickering in the wind. One strong gust, and the flame disappears for Earth. That gust would be the raw energy of the strike, blowing the air into nothingness. Without the atmosphere, there would be no air to breathe, no weather, and no protection. The sky itself would be gone. The speed of these changes is hard to grasp. Earthquakes shake for seconds, storms rage for days, and volcanic eruptions can last weeks. But a strike powerful enough to vaporize the crust, oceans, and atmosphere would finish its work in less than the time it takes to blink. A person standing on the surface would have no warning. One instant, the world would be familiar. The next, it would be gone. Cities, forests, deserts, and rivers would not crumble or burn. They would vanish into vapor. Even underground bunkers or the deepest caves would offer no safety. The energy would pass through them as if they were not there. Think about an asteroid as an example. The asteroid that struck Earth 66 million years ago and ended the age of the dinosaurs was about 6 miles wide. It released energy equal to billions of nuclear bombs and changed the climate for years. But even that did not vaporize the whole planet. For Earth to be stripped bare, the asteroid would need to be much larger, hundreds of miles across, or moving at unimaginable speeds. In that case, the impact would not just create a crater, it would rip away the crust itself. The heat from the strike would be so high that rocks would not melt. They would turn straight into gas. The oceans would boil in an instant, and the air would escape into space. Life as we know it would not have a chance to resist. Cosmic events offer another example. A nearby supernova, the explosion of a dying star, can flood space with radiation and particles. If one occurred close enough, it could strip Earth's atmosphere. If the energy was stronger still, it could vaporize the oceans and crust as well. A gamma ray burst, which is a jet of energy from a collapsing star, could do the same if it were aimed at Earth. These bursts can release more energy in seconds than the sunday will produce in its entire lifetime. If one hit directly, the entire surface of Earth would be erased. To understand the scale, consider numbers. A nuclear weapon might release the energy of tens of megatons of TNT. An asteroid large enough to cause this level of catastrophe could release energy measured in zettajoules, a number with 21 zeros. That much energy applied to Earth in an instant would overwhelm every natural system we depend on. It would not matter if you were at the poles, in the mountains, or on an island. The event would reach every corner at the same time, leaving nothing untouched. Some may wonder if the deeper parts of Earth would remain. The mantle and core would still exist, because the energy required to vaporize them as well would be even greater. But without the crust, oceans, and atmosphere, the planet would no longer resemble Earth. It would be a bare rock surrounded by clouds of gas and dust. It would spin in space as a scarred and empty shell, stripped of the layers that once supported life. Picture the timeline of such an event. The strike happens. In less than a second, the crust becomes vapor. The oceans erupt into clouds of superheated steam. The atmosphere lifts away in a massive plume. The debris spreads outward, glowing from heat. Space around Earth fills with expanding clouds of dust and gas. To an outside observer, Earth would seem to flare like a sudden star before fading into a lifeless ball. For those on the ground, there would be no time to see or feel it. It would be over before awareness could even form. This scenario may sound like science fiction, but the physics behind it is sound. When energy reaches a certain threshold, matter changes state. Solids turn to liquid, liquids to gas, and gases to plasma. The scale of the energy determines how fast and how completely those changes occur on Earth. We only ever see small versions of this process. Lava erupts, water boils, and air shifts in storms. On a global scale, the same process would play out in an instant, but with results that erase all life and structure. The Earth we know would no longer exist. When two massive objects collide in space, the violence does not stay in one place. The impact sends shockwaves across the solar system, changing the balance that holds planets, moons, and asteroids in their paths. Space is not empty in the sense of being still. Every planet orbits the Sunday with precise speed and distance, kept in line by gravity. Even small changes in that balance can set off a chain of motion. When the collision is strong enough, the shock it sends out is not just local. It can ripple across millions of miles, altering the paths of entire worlds. Imagine a stone thrown into a calm pond. The water ripples outward in circles, and anything floating on the surface shifts with the waves. Now replace the stone with two stars colliding, or a large asteroid smashing into a planet. Replace the pond with the solar system, where every planet and moon is a floating object. The shock waves push and pull at them. Some only wobble slightly, while others drift into new paths. Over time, those shifts can become dramatic. The most direct effect comes from gravitational waves. These are distortions in space, time itself, caused when massive bodies move violently. They spread outward like invisible waves. If the collision is between two neutron stars or black holes, the gravitational waves are intense. Planets in nearby orbits feel the tug. Their paths bend slightly, just enough to throw off the delicate balance of years of movement. A small nudge in space can become large when stretched over millions of miles and centuries of time. Earth, Mars, and Venus, for example, keep stable paths now because of a careful balance with the Sunday's gravity. A collision strong enough could tip that balance, pushing Earth closer to the Sunday or farther out toward the cold edges of the system. Moons would feel this disruption too. Take our own moon as an example. It circles Earth in a stable orbit, causing tides and stabilizing our planet's tilt. If a massive collision in the inner solar system shifted Earth's orbit by even a small amount, the moon's path could loosen. It might drift farther away, or worse, break free from Earth's pull entirely. Without the moon, Earth's rotation would wobble, seasons would shift unpredictably, and life would struggle to adapt. For moons around other planets, like the dozens around Jupiter or Saturn, the same principle holds. A slight change in the parent planet's orbit could send moons crashing into each other, colliding with their planet, or drifting into open space. Asteroids would be even more sensitive. The asteroid belt between Mars and Jupiter already teeters in a delicate balance, shaped by Jupiter's strong gravity. A shockwave disrupting Jupiter's orbit even slightly could scatter asteroids. Like marbles spilled across a floor, some would slam into each other, breaking apart into smaller fragments. Others would leave the belt entirely, heading toward the inner solar system. Earth and Mars would then face waves of impacts, each carrying enough energy to destroy regions or even end civilizations. The smooth order of orbits could become a chaotic field of collisions. Comets in the outer solar system would feel it too. They spend most of their time far from the Sunday, but their orbits stretch inward every so often. A disruption in gravity could tug these paths into new shapes. A comet that once passed harmlessly by might instead aims straight at Earth or another planet. Over centuries, the effect would be a system filled with unpredictable impacts. The calm, predictable sky we know would turn into a place of constant threat. An example helps make this clear. Imagine if a collision between two neutron stars happened within a few light years of our system. The gravitational waves would reach us. They would be faint compared to the violence at the source. But even faint waves can shift planetary orbits. Earth's year might grow longer or shorter. The tilt of our axis could change by a degree, enough to alter climate worldwide. Summers could become hotter, winters harsher, and the balance of ecosystems could collapse. Now imagine the same for Mars. If its orbit stretched farther out, its already cold surface would freeze solid, ending the chance for liquid water. If Venus moved slightly closer to the Sunday, its heat would rise to levels even more extreme than today, stripping away what little remains of its atmosphere. Closer to the site of the collision, the disruption would be even more violent. A planet near the blast zone might be thrown out of its orbit entirely. Instead of circling its star, it would wander into deep space as a rogue planet, frozen and alone. Moons would be stripped away. Rings like those around Saturn could scatter. Gas giants could even lose some of their upper layers, torn apart by the force. The system would not collapse all at once, but over years and centuries, the harmony of orbits would break down. The physics behind this is simple. Orbits depend on balance. A planet moves forward, while gravity pulls it inward. The two forces create a path around the Sunday, disrupt that balance with a strong enough push, and the orbit changes shape. A circle becomes an oval, or an oval stretches until the planet escapes entirely. Even a small change in speed or distance can add up over time. A nudge of a few kilometers per h may not seem like much, but across millions of miles, it can shift a planet from safe orbit into a dangerous path. This ripple effect explains why astronomers watch the sky for large impacts and cosmic collisions. They know that the solar system is not fixed forever. It is a set of moving parts, each one sensitive to the others. When one part is struck or shifted, the whole system feels it. A shockwave can carry across billions of miles, reaching the outer edges where Pluto drifts. Even there, orbits can be altered slowly at first, but with lasting results. Think about the solar system as a mobile hanging over a crib. Each planet is a weight hanging from strings, balanced so the mobile moves smoothly. If you tap one side hard enough, the whole mobile swings. Some pieces crash together, others twist out of place. The balance is lost. The same happens in space when a massive collision sends shockwaves outward. On human timescales, the first changes might go unnoticed. A year might become a fraction longer. The distance between planets might stretch, but across thousands of years, those small changes build up. Planets could drift into new positions, moons could break free, and asteroids could scatter. The solar system we recognize today, with its ordered orbits and predictable paths, could turn into a place of chaos, driven by one violent event that sent shockwaves through it all. When two large bodies collide in space, the result is not always destruction alone. Sometimes the violence of the impact creates the raw material for something new. Debris from the crash can gather together under the pull of gravity, and over time, that debris can form a new planet. This is not speculation. The very existence of Earth's moon is believed to come from such an event. Billions of years ago, a Mars-sized object called Theia struck the young Earth. The impact threw molten rock and vapor into orbit, and that material eventually clumped together. Gravity pulled it into a sphere, and the moon was born. The same process that shaped our nearest neighbor can play out on larger scales when planets or planet-sized bodies collide. The key is gravity. After the crash, debris spreads into space. Some pieces fly off at high speed and escape, but most of it remains nearby. Gravity then begins to pull the fragments toward each other. At first, small clumps form, each the size of mountains or islands. These clumps collide and stick together, growing larger. The process is called accretion. Over thousands or millions of years, the clumps merge into a single massive body. If the debris has enough total mass, the result is a planet. This is how scientists believe the planets in our solar system formed in the first place, through countless smaller collisions during the early days of the Sunday. The size of the colliding bodies matters. If two small asteroids hit, they might just break apart, leaving rubble. But if one or both objects are large, like moons or planets, the debris field can be enormous. The more material in orbit after the impact, the greater the chance that gravity will gather it into something new. Imagine smashing two clumps of wet clay together. The pieces scatter, but the larger chunks stick together and reform. On the cosmic scale, the same principle applies, though the timescales and forces are far greater. Temperature also plays a role. When a planet-sized collision happens, the debris heats to extreme levels. Rocks melt into magma, and some even turn into vapor. This molten material can pool together, forming a glowing ball of magma that later cools into solid rock. In this way, the new planet begins hot, its surface molten, much like Earth in its earliest days. Over time, the outer layers cool, solid crust forms, and the planet stabilizes. Whether it develops oceans or an atmosphere depends on what elements the debris contains and how close it ends up to its star. Consider a scenario in the outer solar system. Suppose a large moon of Saturn collided with a stray dwarf planet. The debris might spread out into a disk around Saturn, and over millions of years, parts of that disk could clump into a new moon or even a small planet, if the mass were large enough. The new body might orbit Saturn at first, or it could form in a position far enough away that it circles the Sunday instead. If it does, the solar system would have a new planet, born from violence but shaped into order by gravity. The formation of a new planet is not always clean. The process can leave behind smaller fragments that never merge. These pieces can remain as moons or as asteroid, like bodies trailing the new planet. In fact, the asteroid belt itself may be the leftover material of collisions that never formed a planet. Jupiter's strong gravity may have prevented the debris from accreting fully. This shows how delicate the balance is. Whether debris becomes a planet or stays as rubble depends not just on the mass involved, but also on the gravitational influences of nearby bodies. The example of Earth's moon shows us how enduring such outcomes can be. Without that collision, Earth might never have had a large moon. The moon's presence has shaped tides, stabilized Earth's tilt, and influenced life's evolution. A similar new planet formed elsewhere could also change the dynamics of its system. It might pull smaller asteroids into orbit, clearing dangerous debris from the neighborhood, or it could destabilize nearby orbits, scattering objects into new paths. Each outcome would reshape the system in ways both creative and destructive. The timescale is long compared to human history, but short in cosmic terms. After a collision, the first clumps form within thousands of years. Within millions of years, a new planet could be fully shaped. For comparison, Earth formed over tens of millions of years during the birth of the solar system. In that sense, a planet born from a collision is a kind of second chance at creation, a replay of the forces that built the original worlds. Imagine standing far away, watching through a telescope as such an event unfolds. At first, you would see a bright flash from the collision itself. Clouds of molten rock and dust would expand outward, glowing against the darkness. Over time, the glowing fragments would cool, and you would see a disk of debris circling in space. Centuries later, the disk would begin to thin as clumps merged together. Slowly, one clump would dominate, pulling in the others until a sphere formed. From your vantage point, it would look like a new light taking shape, a planet being born before your eyes. The chemistry of the debris shapes the new world's future. If the material contains water ice and volatile gases, the planet may later form an atmosphere or oceans. If it is mostly rock and metal, the planet may remain barren and airless. In some cases, the impact can strip lighter materials away, leaving behind a dense, iron-rich body. Mercury may be an example of this. Some scientists believe it formed after a large collision stripped much of its lighter crust, leaving a planet with an unusually large core. The diversity of planetary types we see today suggests that collisions and mergers have played a role in shaping many of them. There is also the possibility that such a new planet could sustain life in the distant future. While the immediate aftermath of a collision is violent and hostile, time smooths the chaos. A molten surface cools. Atmospheres can form from volcanic gases or captured debris. If the planet ends up in a stable orbit within the habitable zone of its star, conditions for life could emerge. On Earth, life began not long after the planet cooled and oceans formed. The same could happen on a planet born from the wreckage of another. The story of planetary formation through collisions shows how creation and destruction are linked. What seems like an end can instead be the start of something larger. Two bodies collide, and from their broken pieces rises a new world. Gravity, time, and energy reshape chaos into order. The process is slow and harsh, but the outcome can be a stable planet that lasts for billions of years. In that sense, every world in the sky may carry the history of violent impacts hidden in its past, and every collision may hold the seeds of a new beginning. When a massive body collides with Earth, the aftermath is not just destruction. The impact can send enormous amounts of rock, dust, and molten material into space. Instead of flying off randomly, much of this debris remains trapped by Earth's gravity. It begins to circle the planet, forming a ring of rubble. Scientists believe that this very process created our moon billions of years ago. A Mars-sized object, often called Theia, struck the young Earth with such force that part of the planet's crust and mantle were blasted outward. That material spread into a glowing disk around Earth. Over time, the disk of debris clumped together and coalesced into a single body, the moon we see every night. To imagine this process today, picture Earth immediately after a catastrophic collision. From the surface, the sky would glow with streams of molten rock arching upward. Fragments of the crust and mantle would be torn away and launched into orbit. Some pieces would be tiny grains of dust, while others would be massive boulders. Instead of falling back, they would remain suspended in a chaotic ring, circling Earth at incredible speed. The sight would resemble Saturn's rings, but far more violent in its origin. Instead of icy particles like Saturn's, Earth's ring would be built of shattered stone, metal, and liquid rock, cooled into shards. At first, the debris disk would not look stable. Fragments would crash into each other, breaking apart or sticking together. Each collision would release heat and light, creating a fiery halo around Earth. Gravity would begin to take over. The largest chunks would pull smaller ones toward them. Over thousands of years, these clumps would merge, forming larger and larger bodies. One of these bodies would eventually dominate, sweeping up most of the remaining debris. The result would be a new moon, just as the original moon formed long ago. The scale of such a ring is difficult to picture. It would extend thousands of miles into space, wide enough to stretch across the horizon. From Earth's surface, it would shine brighter than the moon does today, especially in the early years when the material still glowed with heat. At night, the sky would be filled not with stars, but with a glowing arc of debris, circling endlessly. If the collision were recent, the fragments would still be molten, giving the ring a fiery red and orange glow as they cooled. The ring would fade to grey, looking like a ribbon of stone spread across the heavens. This process of forming a debris disk, and later a moon, is a natural consequence of gravity and motion. When an impact occurs, the debris is ejected with great force. Some of it travels too fast and escapes Earth entirely, flying off into the solar system. But most of it falls into a delicate balance, moving fast enough to stay in orbit, but not fast enough to break free. Over time, friction between the particles causes them to settle into a flat disk, much like the rings of Saturn. Within this disk, collisions and mergers slowly build a new world. The timescale of this process is immense compared to human life, yet short on a cosmic scale. In only a few thousand years, the disk could begin to thin as larger clumps absorb smaller ones. Within millions of years, a single body could emerge, stable enough to remain in orbit as a permanent satellite. That new moon would carry the history of its violent birth in its makeup. Its crust, its minerals, and its scars would all trace back to the day of the collision. The example of Earth's moon gives us confidence in this idea. Studies of lunar rocks show they are chemically similar to Earth's mantle, suggesting that the moon was once part of Earth itself. The impact that created it was not a minor event. It reshaped both Earth and its satellite. Earth's tilt may have changed as a result, giving us the seasons we experience today. The moon itself helps stabilize Earth's rotation, keeping the climate relatively steady. Without that ancient debris disk, life might have developed in a very different way, or perhaps not at all. If such an event happened again, the consequences would be profound. A ring of debris forming around Earth would alter the way our planet looks and behaves. Tides would change dramatically as the distribution of mass in orbit shifts the pull on Earth's oceans. The glowing ring would dominate the sky, reshaping the night and possibly outshining the Sunday at dawn and dusk. Over centuries, as the ring collapsed into clumps, impacts from falling debris would continue. Some fragments would not remain in orbit but would rain back down, striking Earth with destructive force. Each impact would scar the surface, adding to the chaos left by the original collision. Beyond the immediate destruction, though, the long-term picture is one of creation. Out of the chaos comes order. The debris settles, gravity shapes it, and a new satellite emerges. Just as the original moon has been a companion for billions of years, so too could a new moon remain, orbiting Earth and influencing tides, seasons, and perhaps even the evolution of life. To visualize this in another way, think of a car crash in slow motion. Pieces of metal and glass fly outward. Some land far away, some crumple together, and some bend back into the wreck. Now expand that image to planetary scale. The crash is violent, the debris immense, but the aftermath is not random. Gravity acts like an unseen hand, gathering the pieces and reshaping them. The wreckage of worlds becomes the seed of something stable and new. This concept is not limited to Earth. Across the universe, moons and planets may form in the same way. Wherever large collisions occur, the result can be a ring of debris that later coalesces. In some systems, that debris might never form a single moon. It may remain as a permanent ring. Like Saturn's in others, one body dominates, sweeping up its neighbors until only one remains. Earth's moon is proof of this process. It is not unique, but an example of how destruction and creation are linked in the story of planets. Standing on Earth in the aftermath of such a collision would mean living under a sky unlike anything we know. The horizon would glow with a ring of stone and fire. Days and nights would change under its light. The familiar moon would be gone, replaced by a newborn halo of debris. For generations, the ring would slowly thin, the pieces merging together. Future observers might witness the birth of a new moon, rising from the chaos of impact and taking its place in orbit. What began as destruction would end as a permanent companion, formed from the shattered pieces of Earth itself. The end of life on Earth would not arrive with warning sirens or long battles for survival. It would come in seconds, faster than human senses could grasp. Every living thing, from the smallest bacteria to the largest whale, would meet the same fate. The cause would be a release of energy so massive that it would erase the conditions needed for life in the blink of an eye. This would not be extinction in the slow sense of species fading away over generations. It would be instant and complete. The ultimate extinction event. Picture the moment of impact if a giant asteroid or planetary body collided with Earth. The surface would light up brighter than the Sunday as shock waves raced outward. Mountains, forests, oceans, and cities would vanish. Heat would spread so quickly that skin, bone, and tissue would not have time to register pain. Entire ecosystems that took billions of years to evolve would be vaporized. Plants would not burn. They would disappear into gas. Animals would not flee. They would cease to exist. Microbes in the deepest soil or at the bottom of the ocean would find no refuge. Even the most resilient forms of life, the extremophiles that thrive in boiling vents or frozen ice, would not withstand the instant rise in temperature and pressure. The atmosphere itself would become unrecognizable. The air we breathe is a fragile blanket, only a few dozen miles thick. In a global catastrophe of this scale, that blanket would lift away in a flash. Oxygen and nitrogen molecules would scatter into space, stripped from the planet. Without air, lungs would collapse, and combustion would stop. Fire, smoke, and ash would not linger, because there would be no medium to carry them. The very act of breathing, which ties every life form to the planet, would end instantly. The oceans would follow the same fate. The Pacific, the Atlantic, the Indian, all would flash into vapor. The water that covers most of Earth's surface would not boil slowly like a kettle left on a stove. It would erupt into superheated gas in less than a second. Fish, whales, and coral reefs would vanish with it. Coastal regions would not flood, because there would be no liquid water left to rise. The hydrosphere, which has shaped climates, weather, and life cycles for billions of years, would be erased in a moment of raw energy. The land itself would not remain. The crust of the Earth, though it feels solid underfoot, is fragile compared to the forces released in such an event. It would crack, shatter, and vaporize. Soil that once grew crops, forests that once covered continents, and deserts that stretched for miles would be gone. The very foundation of human civilization would disappear. Buildings, roads, and machines would offer no protection. Underground shelters and bunkers would be useless, as the heat and pressure would penetrate everything. The idea of survival would lose meaning, because there would be nothing left to survive in. Life has endured mass extinctions before. The asteroid that struck 66 million years ago wiped out the dinosaurs and many other species. Yet even then, life carried on. Birds, mammals, insects, and plants found ways to persist. This scenario is different. It is not about wiping out one branch of life's tree. It is about pulling the tree out by the roots. Every form of life from the surface to the deepest core would be gone. Evolution, which relies on survivors to pass on their genes, would have no raw material left to work with. There would be no seed, no spore, no cell left to rebuild. The speed of this event is what makes it absolute. Normally, extinction plays out over thousands or millions of years. Species decline, habitats shrink, and the slow grind of change ends with disappearance. In an instant extinction, none of that applies. There is no time for migration, no chance for adaptation. The very concept of natural selection fails because there is no environment left for selection to act on. The change is not gradual, it is total. Consider the effect on humans in particular. Our species has adapted to deserts, mountains, jungles, and icy plains. We have built cities in the harshest places and created technology to survive where nature would not allow. Yet in the face of this event, all of that ingenuity collapses. Satellites orbiting Earth would disintegrate. Power grids, machines, and data networks would be vaporized along with their operators. Knowledge stored in libraries and servers would vanish as the medium itself is destroyed. The record of human history would be wiped out, leaving no trace that a civilization ever existed. The event would not only end life on Earth, but also reshape the planet's identity in space. From afar, astronomers on another world might once have seen a blue planet with white clouds and green continents. After the catastrophe, they would see only a bare, glowing sphere, surrounded by a cloud of gas and debris. Earth would appear lifeless, no different from Mercury or the Moon. The signature signs of biology: oxygen in the air, water on the surface, carbon, based compounds in abundance, would be gone. To an outside observer, it would seem as if Earth had never supported life at all. Even if fragments of Earth were cast into space during the collision, they would not carry life with them. Rocks flung into the solar system might drift for millions of years, but without an atmosphere or water, they would be sterile. The concept of panspermia, the idea that life can spread between worlds, would not apply here because there would be nothing left to spread. Every trace of DNA, every protein, every building block of biology would be destroyed in the initial seconds. The own way to understand the magnitude is to compare it with fire. A forest fire can kill thousands of animals and destroy acres of habitat. Yet seeds buried in the soil often survive and life returns. In this case, the fire would not stop at the surface. It would burn through the soil, through the rock, and into the mantle. There would be no hidden seed, no deep refuge. Even the chemical bonds that make up life's molecules would be broken apart. The Earth would be sterilized in a single moment, as if the reset button of biology had been pressed. The phrase, end of life, often sounds abstract, but in this context, it is literal. Every living organism, every ecosystem, every process that defines biology would end together. The food chain would not collapse in steps. It would collapse all at once. Producers, consumers, and decomposers would all disappear. The cycle of life, which depends on energy flowing through countless links, would break instantly. There would be no predators, no prey, no growth, and no decay. The network that connects every organism would be cut, leaving only silence. The ultimate extinction event would leave behind only matter and energy, stripped of the complexity that life brings. What once teemed with diversity and interaction would become uniform and empty. The timeline of biology on Earth would stop in seconds, closing a story billions of years in the making. The world would remain as a planet of rock and metal, but without breath, movement, or growth. It would be Earth in name only, a place where life once flourished, but no longer exists. When a massive object collides with Earth, the damage does not stop at the surface. The atmosphere, the thin layer of gases that makes life possible, can be blown away by the sheer force of the impact. Scientists call this process atmospheric blow. It happens when the energy of the collision is so great that it launches large amounts of air into space, stripping the planet of its protective cover. The atmosphere is fragile compared to the solid body of Earth. While the crust is miles thick and oceans stretch deep, the atmosphere extends only a few dozen miles before fading into space. A sudden burst of energy from a major impact can tear it off in seconds. Imagine dropping a rock into a glass of water. The splash carries droplets into the air, some flying far away from the glass. An asteroid strike works in a similar way, except the splash is not water, but air itself. When the impact occurs, the explosion sends shockwaves through the atmosphere. These waves push gas outward at such high speeds that some molecules reach escape velocity, the speed needed to leave Earth's gravity behind. Once gone, they cannot return. The result is a thinner, weaker atmosphere, or in extreme cases, a planet stripped almost bare. To understand how serious this would be, consider what the atmosphere does. It keeps oxygen available for breathing. It shields the surface from harmful radiation. It holds in warmth, creating the greenhouse effect that keeps Earth from freezing solid. It also protects us from smaller asteroids, burning them up before they hit the ground. Air pressure would drop so low that human lungs could not function. Water on the surface would boil away into space. Plants and animals would suffocate within moments. The scale of blow-off depends on the size and speed of the impactor. A small asteroid like the one that ended the dinosaurs' reign would throw dust and ash into the air, but would not strip the atmosphere entirely. A much larger body, perhaps hundreds of miles wide, would release enough energy to send entire sections of the atmosphere into space. The difference is like lighting a firecracker compared to detonating a nuclear bomb. Both cause blasts, but one shakes only a small area while the other levels a city. On a planetary scale, the larger the strike, the greater the loss of air. Mars gives us a real-world example. Long ago, scientists believe Mars had rivers, lakes, and even oceans. But then it lost most of its atmosphere. Some of that loss came from solar wind, the constant stream of charged particles from the Sunday. Without a strong magnetic field, Mars could not hold on to its air, but impacts also played a role. Large asteroids struck Mars, each blow peeling away part of its atmosphere. Over time, the air grew thinner until liquid water could no longer stay stable on the surface. Mars became a dry, cold world. A similar event on Earth would push our planet down the same path. Picture the immediate effects of such a blow-off. The sky would flash as the impact sent shockwaves racing outward. Within seconds, vast amounts of air would be lifted into space. The blue sky would fade to a dim, hazy layer. Pressure on the surface would collapse. A person standing outdoors would feel their chest tighten as the air thinned. Water would hiss into vapor, rivers and lakes vanishing into clouds that themselves drifted into space. Fires might ignite from the heat, but they would sputter out quickly as oxygen disappeared. Even if the atmosphere were not fully lost, the damage would still be catastrophic. A thinner atmosphere would mean weaker shielding against cosmic radiation. The Sunday's ultraviolet rays would reach the surface with lethal intensity. Without enough greenhouse gases, temperatures would plunge, leaving Earth frozen. Or, if greenhouse gases dominated what little air remained, the planet could overheat. Either way, the balance needed for life would be gone. The process does not end with the initial strike. After the impact, Earth would be surrounded by a cloud of debris, rock, dust, and gas launched into orbit. Some of this material would fall back. Some would combine with what remained of the atmosphere, creating toxic conditions. Acid rain formed from vaporized rock and chemicals could fall on the surface. The recovery of the atmosphere would not be quick. It could take millions of years for volcanic activity to release enough gas to rebuild a stable layer, if at all. During that time, the surface would remain hostile. Think about what happens when astronauts step outside their spacecraft without a suit. Their bodies cannot handle the vacuum of space. Fluids boil, lungs collapse, and death comes in moments. A planet stripped of much of its air would resemble that vacuum. Humans and animals could not adapt fast enough. Even underground shelters would fail, because without air pressure above, the environment inside would eventually leak away. Survival would be measured in seconds, not hours. The oceans would also be affected. With the atmosphere gone, the balance between liquid water and air pressure would vanish. Lakes and seas would begin to boil. not because of heat, but because of pressure loss. Molecules of water would escape directly into space as vapor. Earth's blue oceans, which have existed for billions of years, would shrink and disappear. Over time, only ice locked deep underground or near the poles might remain. Asteroids are not the only cause of atmospheric blow-off. A nearby cosmic explosion, such as a supernova or gamma ray burst, could strip Earth's air with radiation and high-energy particles. The effect would be the same: the sudden removal of the protective blanket we depend on. Unlike an impact, where debris might one day rebuild the atmosphere, radiation stripping leaves little chance for recovery. To picture the scale of this destruction, compare it to the act of popping a balloon. The rubber holds in air, but one puncture, and the air escapes into the room. Earth's atmosphere works the same way. Gravity holds it in place. But if the balance is disrupted by enough force, the air escapes into the larger vacuum of space. The difference is that the room in this case is infinite, and once the gases leave, they never come back. Everyday life on Earth depends on the quiet presence of air around us. We breathe it, weather flows through it, and it shapes the colors of the sky. Yet it is far more fragile than most imagine. A single massive impact could erase it in seconds, leaving Earth bare and lifeless. The ground would remain, the oceans would boil away, and the air would vanish. What was once a living planet would look more like Mars, stripped and silent under the weight of space. When a massive impact strikes Earth with enough energy, the solid surface no longer stays intact. The crust melts, flows, and spreads until the planet is covered in an ocean of molten rock. Scientists call this a magma ocean, and it is one of the most extreme states a planet can reach. It is not water. It is not lava flowing from a single volcano, but a continuous global sea of liquid rock, heated to thousands of degrees. The Earth itself becomes unrecognizable, transformed into a glowing sphere where continents and oceans no longer exist. The process begins with the impact. When a planetary body collides with Earth, the energy of motion converts into heat. The larger the object and the faster it moves, the more energy is released. At a certain threshold, the heat is enough to melt rock, mountains, valleys, and plains no longer matter. Because all solid structures lose their form, the crust softens and then liquefies, merging into a vast pool of magma. Picture a frozen lake in spring. As the ice melts, cracks spread, and the surface breaks apart into liquid water. Replace ice with stone and water with magma, and you have a sense of how solid ground becomes a molten ocean. The temperature of such a surface would rise beyond what humans can comprehend. Ordinary lava that erupts from volcanoes on Earth today flows at about 1,200 degrees Celsius. A magma ocean could reach twice or even 3 times that temperature. At those levels, not only does rock melt, but many minerals vaporize, turning into gas. The air above the surface would fill with glowing clouds of rock vapor, creating a toxic and scorching atmosphere. The ground would not be safe to stand on because there would be no ground, only liquid rock stretching as far as the eye could see. The depth of a magma ocean could be staggering. Instead of being a thin layer of molten rock, it could extend for hundreds of kilometers into the mantle. In the earliest history of Earth, scientists believe the planet was almost entirely molten after it formed. Over time, the outer layers cooled and a crust hardened, but a massive impact could reset that process. Melting the surface all over again, the planet would glow red and orange, much like the images of newly formed exoplanets we sometimes detect with telescopes. From space, Earth would appear as a glowing orb, more like a small star than a rocky planet. This kind of environment would erase everything that existed before. Oceans of water would not survive. They would boil away instantly, adding steam to the superheated atmosphere before disappearing into space. Forests, deserts, cities, and mountains would all dissolve into molten pools. Even the highest peaks like Everest would be meaningless, swallowed by liquid rock. The biosphere, the thin layer of life covering the planet, would be destroyed without a trace. The energy released would sterilize Earth, leaving only magma, gas, and fire. To make the scale more relatable, imagine standing near a volcano as it erupts. The sight of glowing lava flowing down a slope is overwhelming. The heat is intense, the air smells of sulfur, and the ground trembles. Now imagine that instead of a single eruption, the entire surface of Earth looks like that. No cool rock, no stable soil, no flowing rivers, only endless glowing seas of magma. From horizon to horizon, the planet would shine with molten rock. Volcanoes would no longer exist as separate features, because the whole Earth would be one giant volcano. Over time, the magma ocean would not stay still. Convection currents would churn through the molten material. Hot magma from deep inside would rise, while cooler magma near the surface would sink. This movement would keep the surface restless, with waves and currents of liquid rock moving like the tides of an ocean. Unlike water, though, these waves would be thousands of degrees hot and heavy with molten minerals. Imagine waves taller than skyscrapers made not of water, but of glowing, flowing stone. The planet would never be calm under such conditions. The atmosphere would also change dramatically. Gases released from vaporized rock and boiling seas would form a thick, toxic envelope. Carbon dioxide, sulfur dioxide, and water vapor would dominate. Lightning would flash through clouds of ash and vapor. The sky would glow with reflected light from the magma below. Breathing would be impossible, and visibility would be reduced to a fiery haze. In this environment, even machines would not survive long. Metal would melt, electronics would fail, and no structure could resist the heat. The cooling of a magma ocean is slow. It would take millions of years for the surface to lose enough heat for solid crust to form again. During this time, the planet would radiate energy into space. From far away, as the magma ocean slowly hardened, lighter minerals would rise to form a crust, while heavier ones would sink deeper into the mantle. This process, called differentiation, is how planets develop layers of crust, mantle, and core. In that sense, a magma ocean is not only destructive, but also a step in planetary creation. It reorganizes the planet from top to bottom, leaving behind a new structure once it cools. Zone example comes from the Moon. Scientists believe the early Moon once had a magma ocean covering its surface. Evidence from lunar rocks shows that lighter minerals floated upward, creating the crust we see today, while denser minerals sank. The same process could happen on Earth. Once the magma cooled, the planet would have a new crust, a reorganized mantle, and possibly new continents waiting to form. The cycle of destruction and creation is written into the very surface of planets. The sheer violence of this process underscores how fragile the conditions for life are. The crust and oceans we depend on exist only because Earth has cooled for billions of years without being reset by another planet-sized collision. If such an event occurred again, life as we know it would not endure. The planet would survive, but it would be transformed into a glowing sphere of molten rock, its history of life erased under the waves of a magma ocean. To imagine the human perspective, consider how little time there would be to react. At the moment of impact, shock waves would melt the crust almost instantly. In less than a second, the ground would liquefy, and oceans would flash into vapor. From space, astronauts on a nearby station would see Earth ignite, glowing brighter than it ever had before. From the surface, no one would survive long enough to even see the transformation. The shift from solid ground to molten ocean would be immediate and final. The concept of a magma ocean reveals both the power of impacts and the resilience of planetary systems. While such an event would mark the end of all life and civilization, it would also reset Earth in a way that could, over millions of years, allow for a new surface to form. The balance of rock heat and gravity ensures that the planet continues even after being reduced to liquid stone. A world that once had seas, forests, and skies would become an ocean of magma, rolling and glowing until the slow passage of time cooled it once again. When two massive bodies collide in space, the result is not only heat and shockwaves. A violent burst of radiation can also be unleashed, flooding the surrounding region with deadly energy. Radiation in this context is not the gentle warmth of sunlight or the glow of a fire. It is high-energy particles and electromagnetic waves that can tear apart molecules, damage DNA, and strip atmospheres from planets. The burst is sudden, powerful, and far-reaching. In such an event, survival is impossible for anything caught nearby. The source of this radiation is the sheer amount of energy released during impact. When objects the size of moons or planets crash, much of their kinetic energy converts into heat and light. But a significant portion is released as radiation, gamma rays, X-rays, and streams of charged particles spread outward at the speed of light. These forms of radiation carry energy far beyond what ordinary sunlight delivers. A person standing unprotected would not feel a warm glow. Instead, their cells would be destroyed almost instantly, as if every molecule in their body were under attack. Imagine the difference between standing near a campfire and standing in front of an atomic blast. A fire warms your skin, but a nuclear detonation bathes everything in a wave of radiation that causes burns, sickness, and death. Now multiply that nuclear event by billions, and you begin to approach the level of energy a cosmic collision could release. Radiation from such an impact is not confined to a single spot. It travels across space, bathing entire planets or star systems in its destructive light. Earth itself has experienced lesser versions of radiation bursts. Solar flares and coronal mass ejections from the Sun send waves of charged particles toward us. Our atmosphere and magnetic field shield us, protecting life on the surface. Without those defenses, these smaller bursts would already make Earth uninhabitable. A collision in space, however, would dwarf any solar flare. If Earth were close to such an event, the protective shield would not matter. The energy would overwhelm it, stripping away the atmosphere and irradiating the surface in seconds. The scale of damage depends on distance. If the burst happens light years away, Earth might see only a faint ripple, like a flash of light in the night sky. But if it occurs within our own solar system, the consequences are final. At close range, the radiation dose would be so extreme that even underground or underwater shelters would offer no safety. Radiation penetrates solid material, breaking down molecules regardless of barriers. Life would not die slowly, it would collapse instantly, undone by invisible energy moving too fast and too powerfully to resist. Gamma ray bursts offer a real-world comparison. These bursts occur when massive stars collapse or when neutron stars collide. For a few seconds, they release more energy than our Sun will produce over its entire lifetime. If one were to occur near Earth, it would sterilize the planet. The collision of neutron stars, in particular, is thought to produce both gravitational waves and radiation bursts. Such events show us that the universe already holds the power to end life with radiation alone. A planetary collision near Earth would create the same kind of lethal burst, only on a scale tied directly to our neighborhood in space. To understand the effects on biology, consider what radiation does to cells. At low levels, like those used in medical imaging, it passes through tissue but causes little harm. At higher levels, such as those from nuclear accidents, it breaks DNA and proteins. leading to sickness and death. A cosmic radiation burst is far beyond those scales. The dose would be so high that cells would be destroyed before they could even attempt to repair themselves. Plants, animals, and microbes alike would disintegrate at the molecular level. No species would escape, no matter how resilient. Even extremophiles, which survive boiling vents and radioactive waste on Earth, would find their limits exceeded. Radiation also interacts with the atmosphere. When high-energy particles strike molecules of nitrogen and oxygen, they break them apart. This destroys the ozone layer, which normally shields Earth from ultraviolet light. Without ozone, harmful solar radiation would bombard the surface continuously. Even after the initial burst, the long-term damage would keep Earth sterile. Oceans would heat under the unfiltered rays, land would scorch, and no new life could take root. The oceans themselves would not provide shelter. While water blocks some radiation, the intensity of a burst from a planetary collision would penetrate deep fish, coral reefs, and deep sea creatures would all die. Even if fragments of life tried to cling to survival in the darkest depths, the collapse of ecosystems above would remove every link in the food chain. Radiation kills not only directly, but also indirectly, by stripping away the systems that support life. So picture the suddenness. Imagine a flash brighter than the Sunday appearing in the sky. In that instant, radiation spreads outward, faster than thought, faster than sound. In cities, forests, and oceans, every living thing is struck at once. There is no time to hide, no warning to prepare. Within seconds, Earth is silent. From space, the planet might still appear intact, but its surface would be lifeless. The oceans would steam, the land would darken, and the atmosphere would shimmer with ionized gases. The reach of such an event extends beyond Earth. Other planets in the solar system would feel it too. Mars, with its thin atmosphere, would be sterilized more quickly than Earth. The gas giants, though massive, would lose parts of their upper layers to radiation-driven chemistry. Moons with icy surfaces like Europa and Enceladus would have their fragile shells altered. Even the asteroid belt would be stripped of volatile materials. The entire solar system could be reshaped by a single burst of radiation from one collision. The energy involved makes survival impossible not only for life but also for technology. Satellites would fail as their electronics fried under the particle storm. Spacecraft would be disabled, communication networks silenced. Even probes sent to distant planets would stop functioning, their circuits destroyed by radiation exposure. Human technology, like human biology, is fragile in the face of such extremes. The memory of civilization stored on servers and machines would be erased as quickly as life itself. In thinking about these bursts, it is important to see them as natural consequences of extreme violence in space. Matter and energy are tied together by the laws of physics. When mass collides at high speed, the result is not only heat and shock waves, but also radiation spreading outward at light speed. The invisible burst is as destructive as the visible fireball on a world like Earth, where life depends on a narrow range of conditions. Such a burst ensures that survival is impossible. A radiation burst from a planetary collision is the final expression of energy released without limit. It strips air, sterilizes oceans, destroys DNA, and erases both life and technology. The planet itself may remain glowing and molten, but the signature of biology vanishes in seconds. What is left is a silent, irradiated world, bearing the mark of an event too powerful for anything living to endure. The solar system is a place of balance held together by gravity. Every planet, moon, and asteroid follows a path that depends on the pull of the Sunday and the combined masses of its neighbors. Earth has its place in this system, circling the Sunday at a steady distance, with its own gravity tugging on the moon and even pulling slightly on other planets. If Earth's mass were to change, Or if the planet itself were relocated after a massive collision, the balance of the solar system would shift. Even small changes in mass or position can ripple outward, altering the orbits of planets and reshaping the harmony that has existed for billions of years. To see why, think about the solar system as a kind of cosmic machine. The Sunday sits at the center, its gravity acting like the main gear. The planets are smaller gears, turning around it. Each planet also tugs on the others, creating a network of pushes and pulls. This system is delicate. A change in the size or weight of one gear, or its position, affects how the others turn. Earth's mass is only a fraction of the Sunday's, but it is still enough to influence nearby bodies like the Moon, Venus, and Mars. If Earth suddenly lost part of its mass after a violent impact, its gravitational pull would weaken. The Moon, instead of circling at its familiar distance, might drift farther out or even break free. Mars and Venus might shift slightly as well, their orbits responding to the new pattern of gravity. Relocation of Earth would be even more dramatic. Imagine if a collision nudged Earth closer to the Sunday. The change might seem small, perhaps only a few million miles, but the results would be immense. A closer orbit would mean higher temperatures, stronger solar radiation, and faster orbital speed. Seasons would change, and the balance of energy in the inner solar system would tilt. Venus, already a hot planet, might be pushed into greater instability if Earth's new orbit interfered with its gravitational rhythm. Mars, on the other hand, might feel a shift in its distance from Earth, which could affect the delicate patterns of its own orbit over time. If Earth moved outward instead, the opposite would occur. The planet would cool as it drifted farther from the Sunday. The tug Earth exerts on other planets would weaken with distance, and this could change the arrangement of the asteroid belt between Mars and Jupiter. Even Jupiter itself, the giant of the solar system, responds to small nudges from its neighbors. Though its mass dwarfs Earth's, tiny changes can build up over millions of years, causing new resonances in the orbits of smaller bodies. A useful way to picture this is by thinking about a tightrope walker carrying a pole. The walker stays balanced because the weight of the pole spreads out evenly. Now imagine part of the pole breaking off or shifting to one side. The walker wobbles and has to adjust. In the solar system, the Sunday is the tightrope walker, and the planets are the weights of the pole. If Earth's mass were reduced or shifted, the balance of the system would wobble, and the other planets would adjust their orbits in response. The changes might not be obvious right away. Orbits are long, and shifts take time to reveal themselves. A slight alteration in Earth's mass could take thousands of years to show a noticeable effect on Mars or Venus. But gravity is patient, and even the smallest difference accumulates over time. What begins as a fraction of a degree in orbital tilt can eventually become a major drift. A planet that once circled in harmony with the others might find itself on a path that crosses their orbits, raising the chance of future collisions. History gives us examples of how sensitive orbital balance can be. The early solar system was chaotic, filled with collisions and shifts in mass. Scientists believe that the orbits of Jupiter and Saturn may have migrated during that time, their movements scattering asteroids and even flinging smaller planets out of the system entirely. Earth itself may have been struck by Theia, the impact that created the Moon. That collision not only reshaped Earth, but also influenced the long-term balance of the system. The fact that we have a stable set of orbits today is the result of billions of years of adjustments after such violent beginnings. If Earth's mass were reduced by a collision that stripped away its crust or atmosphere, the immediate effect would be local, but the long-term effect would echo across the system. The Moon might become unstable, drifting outward until it escaped Earth's pull. Without the Moon, Earth's tilt could wobble, changing climates and seasons. The loss of mass would also weaken Earth's pull on asteroids. possibly sending some drifting into the inner solar system, where they could pose a threat to Mars or Venus. Over millions of years, the orbits of neighboring planets would shift slightly, rewriting the structure of the inner solar system. On the other hand, if a collision added mass to Earth, perhaps by merging it with another large body, the opposite problem would occur. A heavier Earth would pull harder on the Moon, possibly drawing it closer. Over time, this could lead to tidal heating so extreme that the Moon's surface would crack and shift. A larger Earth would also tug more strongly on Venus and Mars, changing their orbits little by little. Even Jupiter could feel a faint pull, and its immense gravity would amplify the effect, spreading it across the outer solar system. The Sunday itself would not remain completely untouched. Although Earth's mass is tiny compared to the Sunday's, the center of mass of the solar system, the barycenter, would shift slightly if Earth's position or weight changed. Right now, the Sunday does not sit perfectly still at the center of the system. It wobbles slightly due to the pull of the planets, especially Jupiter. A change in Earth's mass or orbit would add to that wobble, creating a new balance point. Though the shift might be small, it would ripple outward, affecting the paths of other bodies another way. To picture this is by looking at the rings of Saturn. Each piece of ice and rock in the ring's orbits because of Saturn's gravity, but the moons nearby also tug on them. If one moon were to gain or lose mass, the rings would shift and new patterns would emerge. The solar system works in the same way. Earth is not as large as Jupiter or Saturn, but its presence still helps shape the balance of the whole system. Changing its mass or moving its orbit would be like shifting one of Saturn's moons. The ripple effect would travel far and wide. Over very long timescales, the balance of the solar system is never perfect. Planets interact with each other constantly, their orbits drifting slightly. But a sudden change in Earth's mass or orbit would speed up those drifts and possibly destabilize the entire system. The inner planets might collide after millions of years, or asteroids could be thrown into chaotic paths. The balance we take for granted is the result of precise relationships. Alter one of those relationships, and the system must find a new order, even if it takes eons to do so. In this way, the fate of Earth is not only about the planet itself, but also about its role in the solar system. A change in its mass or location is not isolated. It changes the dance of gravity that binds the planets together. Even the Sunday, the anchor of the system, would feel the shift. What begins with Earth could spread to Mars, Venus, and beyond, rewriting the structure of the solar system, one orbit at a time. When a planet suffers a violent collision, it does not always remain whole. The energy of the impact can shatter it into countless fragments, some small as dust and others large as mountains. These broken pieces do not vanish. Instead, they continue traveling through space, each one caught in the web of gravity that defines the solar system. What was once a single planet becomes a swarm of fragments, each with a new orbit of its own. Over time, these pieces may resemble asteroids, like bodies, wandering through space in paths set by the force of the impact and the pull of nearby planets and the Sunday. The process begins at the moment of destruction. An object striking a planet releases energy, so intense that rock, metal, and soil are hurled outward at high speed. Some fragments escape the planet's gravity entirely, flung into space to drift independently. Others remain nearby, circling in chaotic orbits that may eventually settle into more predictable paths. The size and speed of each fragment determine where it will end up. A small shard may be drawn back into the planet, falling as molten debris. A larger piece moving fast enough might slip into its own orbit around the Sunday, joining the ranks of asteroids and comets already drifting there. The solar system provides examples of this process. The asteroid belt between Mars and Jupiter may be the remains of a planet that never fully formed, shattered by collisions early in the system's history. Instead of coalescing into one body, the fragments stayed scattered, each one following its own orbit around the Sunday. Similarly, many irregular moons orbiting planets today are thought to be captured fragments, pulled in after impacts sent them drifting through space. The evidence suggests that when planets break apart, their fragments do not disappear. They become part of the ongoing structure of the solar system. The orbits of these fragments depend on speed and direction. If a shard of rock is ejected directly outward, it may travel in an elongated orbit, swinging far from the Sunday before returning. If another fragment is pushed sideways, it might circle in a wide, stable loop. Some pieces may end up in paths that cross other planets, setting the stage for future collisions. Over millions of years, these fragments could strike Mars, Venus, or even Earth itself, repeating the cycle of destruction on a smaller scale. Others might remain stable for billions of years, drifting quietly as new members of the asteroid population. The scale of the debris field would be immense. Imagine a planet the size of Earth breaking into fragments. Each chunk could be the size of a city or even larger. Together, they would spread across space, forming a trail like the debris of a shattered ship drifting in the ocean. From a distance, the system would appear cluttered, filled with glowing fragments, reflecting sunlight as they spun on their paths. For any surviving observers, the night sky would no longer look familiar. Instead of a few bright planets, the heavens would swarm with dozens or hundreds of new objects, each one a reminder of the catastrophe. The gravitational pull of other planets would shape the long-term fate of these fragments. Jupiter, with its immense gravity, has a history of capturing stray bodies and pulling them into orbit or flinging them into the outer solar system. Fragments from a shattered planet might find themselves drawn into Jupiter's influence, becoming part of its complex system of moons and rings. Others could be ejected completely from the solar system, turned into rogue asteroids wandering the galaxy. The randomness of these paths makes the aftermath of a planetary breakup unpredictable. Collisions among the fragments themselves would also be common. As shards crossed paths, they would smash into each other, breaking into smaller pieces. Over time, the sharp edges would wear down, and the debris field would settle into smaller, more stable orbits. Some fragments might merge again, creating new bodies large enough to resemble dwarf planets or large asteroids. This process of destruction and recombination echoes the early history of the solar system, when planets first formed from smaller pieces colliding and sticking together. In this way, the fragments of a shattered planet might one day create new bodies, continuing the cycle of planetary birth and death. The danger of such fragments is not limited to their own region of space. A shard on the right trajectory could wander into Earth's orbit, striking our planet with devastating force. The history of Earth already shows evidence of such impacts. Craters scattered across the globe are scars from collisions with objects that were once fragments of larger bodies. If an entire planet were shattered, the chances of impacts would rise, with countless fragments crossing paths with Earth over millions of years. Each encounter would be another reminder of the catastrophe that set the fragments free. To visualize this, imagine a shattered mirror. Each piece reflects light, and together they scatter brightness in many directions. A shattered planet works in a similar way. Each fragment reflects sunlight, making the sky filled with wandering points of light. Some would move predictably like planets, while others would dart unpredictably, shifting as they collided or passed close to larger bodies. From Earth, such a scene would look chaotic, a solar system no longer in neat order, but filled with reminders of destruction. The timescale of this process stretches across millions of years. In the short term, fragments race outward, glowing from the heat of the impact. In the medium term, orbits stabilize, with some fragments falling back, others captured, and many drifting as independent asteroids. In the long term, new structures may form: a cluster of moons, a new asteroid belt, or even a small planet built from recombined pieces. The solar system is dynamic, and the aftermath of a shattered world would not be static, but ever changing, shaped by gravity, collisions, and chance. Examples beyond our solar system support this picture. Observations of young stars often show disks of dust and debris, believed to be the remnants of violent collisions. Around some stars, astronomers have seen evidence of planets breaking apart, their fragments scattering in wide arcs. These systems show that the process of planetary shattering and fragment orbiting is not rare. It is part of the natural evolution of planetary systems across the galaxy. The fate of the fragments is as varied as the paths they take. Some may endure as asteroids for billions of years, silent travelers orbiting the Sunday. Others may collide and merge, becoming the seeds of future worlds. Some may fall into the Sunday itself, vanishing in a final burst of heat. The story of shattered planetary pieces is not just about destruction, but also about the rearrangement of matter in space. What was once a single body becomes many, each with its own orbit, each carrying the history of the impact from the perspective of life on Earth. These fragments represent both a warning and a reminder. A shattered planet's pieces could cross our path, bringing impacts and chaos. But they also show that the solar system is not fixed. It is alive with change. And every orbit, every asteroid, and every moon may once have been part of something larger. In that sense, the fragments of a destroyed planet are not simply rubble. They are travelers with new orbits, telling the ongoing story of how worlds are broken and remade. When a massive impact tears a planet apart or ejects huge amounts of material into space, not all of that debris escapes into the void. A large portion stays close, held in place by the planet's gravity. Instead of falling back immediately, the fragments can spread into orbit, forming a disk of rubble. Over time, the disk begins to organize itself. Small pieces collide, merge, and clump together. Larger chunks pull smaller ones into their orbit. This process, called accretion, can eventually create stable satellites. In other words, a single catastrophic impact has the potential to create not just one moon but several. The best-known example is our own moon. Scientists believe that billions of years ago, Earth was struck by a Mars-sized body called Theia. The collision blasted molten rock and vapor into orbit. That material did not scatter randomly, but collected into a glowing disk around Earth. Within a short span of geologic time, gravity shaped the fragments into one large body, the Moon. But while Earth ended up with a single major moon, the same process could just as easily produce more than one. To picture how this might happen, imagine throwing handfuls of wet clay into a spinning bowl. Some lumps stick together right away, while others bounce, spin, and settle into separate clumps. If the clay keeps moving in the bowl, several distinct blobs form, each on its own path in space. The bowl is the planet's gravity, and the clumps are the building blocks of moons. Depending on the amount of debris and how it spreads, the end result could be multiple moons of different sizes. Look at Mars for an example in miniature. Mars has two small moons, Phobos and Deimos. They are irregularly shaped, more like captured asteroids than spherical bodies. But they may have formed from debris after a large impact on Mars. Instead of merging into one object, the fragments settled into two separate orbits. This shows that a planet does not always produce a single moon. The final number depends on how the fragments move, how they collide, and whether gravity allows them to remain stable over long periods. The formation of multiple moons is a story of balance. Each piece of debris feels the pull of the planet, the tug of nearby fragments, and the influence of larger bodies like the Sunday or nearby planets. If two clumps get too close, one may crash into the other, or one may be ejected into space. But if they remain at the right distances, they can each settle into stable orbits. Over millions of years, the system of moons can become as permanent as our single moon is today. Jupiter and Saturn provide other insights. Their dozens of moons may not all have formed in one event, but their presence shows how common multiple moons can be. A giant impact on a smaller planet would not create as many satellites as Jupiter's gravity allows. But the principle is the same. Enough debris and enough time can yield several stable moons. Each one may be different in size, shape, and composition. Some might be tiny, only a few kilometers across, while others could grow large enough to rival Earth's moon. The surface of a planet after such an event would be forever changed. Imagine looking up at the night sky after a massive impact had formed new moons. Instead of one bright companion rising and setting, there could be 2, 3, or more. Some might be close, appearing large in the sky, while others would be distant, shining as small orbs. Their cycles would differ, creating overlapping patterns of phases. Eclipses would become more common as one moon passed in front of another or crossed the rhythm of tides would change as well, with multiple pulls on the oceans creating complex patterns of rise and fall. If life still existed after such a catastrophe, it would feel the effects directly. The gravitational tug of several moons could make tides higher and less predictable. Animal behaviors tied to the cycles of a single moon would face disruption. Nights would rarely be dark, as the combined light of several moons would brighten the sky. The cultural impact on human life, if humans were present, would be profound. Myths, calendars, and navigation would all adapt to a sky filled with many companions instead of one. From a physical standpoint, the creation of multiple moons also raises the chance of long-term instability. Moons tug on each other as well as on the planet. If their orbits overlap or resonate, they may eventually collide or be flung away. Some moons may not survive for billions of years. They may fall back to the planet's surface, causing secondary impacts. Others may drift farther out until they escape entirely, becoming rogue bodies in orbit around the Sunday. The moons that remain stable, though, could last for eons, permanent reminders of the impact that created them. The chemistry of the debris plays a role as well. A disk made mostly of rock would form solid, airless moons. If the debris included ice, the resulting moons might be lighter, more reflective, and possibly capable of holding subsurface oceans, if conditions allowed, around a smaller planet. The moons might be small and irregular. Around a larger planet, they might grow large and spherical, shaped by their own gravity. Each moon would carry the signature of the original collision in its makeup. In other planetary systems, we see signs of similar processes. Telescopes have spotted disks of dust around young planets, likely the raw material for moon formation. Some exoplanets may host not just one large moon, but entire families of satellites, born from violent impacts. The same processes that shaped our moon are at work throughout the galaxy. The possibility of multiple moons forming from one catastrophic event is not rare. It is part of the natural cycle of planetary evolution. The time needed for moons to form from debris is short in cosmic terms. Within thousands of years, clumps of rock would grow large enough to clear their orbits. Within millions of years, the system would stabilize, leaving behind one or several moons compared to the billions of years that planets last. This is a rapid process. A catastrophic collision might end life in an instant, but it would also set the stage for new moons that could last for the rest of the planet's history. The sight of several moons orbiting a planet would be striking. From the surface, each one would rise and set on its own schedule. Sometimes two might appear in the sky together, glowing side by side. Other times, one might vanish behind the other in a dramatic eclipse. The shifting light and gravity of multiple moons would make the planet's environment unlike any we know on Earth today. Such a sky would serve as a constant reminder that even out of destruction, new structures can emerge. In this way, a single catastrophic event has the power to reshape not only a planet's surface, but also its skies. The fragments that survive in orbit can create a family of moons, each carrying the history of the impact in its composition and its path. The result is a transformed world, its nights forever changed by the presence of multiple companions circling above. When a planet breaks apart after a violent collision, the story does not end with its own destruction. The fragments scattered into space do not remain in place. They travel, pushed by the force of the impact and guided by gravity. Over time, some of these fragments find new paths that intersect with other planets. The result is a chain of impacts that can reshape not only the shattered world but also its neighbours. Mars, Venus, and Jupiter sit close enough to Earth that they would be at risk if such a catastrophe occurred here. Each of them would feel the consequences in ways that could alter their surfaces, atmospheres, and even long-term histories. Mars lies just beyond Earth's orbit, a small, cold planet with a thin atmosphere. If fragments from a destroyed Earth shot outward, many would pass near Mars. Some would strike its surface at speeds far greater than anything we see from ordinary meteors. The thin Martian atmosphere offers little protection, so fragments would reach the ground intact. Each strike would gouge deep craters, throwing dust into the air and reshaping landscapes. The dust could linger, blocking sunlight and cooling the planet even further. If Mars had any hidden water near the surface, the heat from these impacts could melt it, creating temporary floods that freeze again once the dust settles. Over time, repeated strikes might strip away what little atmosphere Mars still holds, leaving it even more barren. Venus, by contrast, has a thick atmosphere of carbon dioxide and clouds of sulfuric acid. Fragments falling toward Venus would burn brightly as they entered, creating fireballs that lit up the sky. Large pieces, however, would survive the plunge and slam into the surface, sending shockwaves through the crust. The atmosphere would trap the heat, raising surface temperatures even higher for a time. Venus already has a runaway greenhouse effect, with heat trapped under its dense clouds. A rain of fragments could push that effect to new extremes, adding enough energy to melt parts of its crust or trigger massive volcanic eruptions. In this way, debris from a shattered planet could make an already hostile world even more unstable. Jupiter is different again. Its massive gravity acts like a net, pulling in objects that pass nearby. Many of the fragments from a destroyed planet would eventually be captured by Jupiter. Some would burn up in its upper atmosphere, adding streaks of light as they plunged into the gas giant. Others would penetrate deeper, releasing energy in explosions more powerful than nuclear weapons. The scars of such impacts can last for years. In 1994, astronomers saw this happen when fragments of the comet Shoemaker, Levy 9, crashed into Jupiter, leaving dark marks larger than Earth itself. If a planet shattered near Jupiter, the gas giant would catch many of its pieces, and the impacts would create storms and scars across its surface. These events would not change Jupiter's structure, it is too massive, but they would reshape its atmosphere for decades. The effect on these planets would not be limited to surface or atmospheric changes. The fragments could alter orbits as well. A massive piece striking Mars might shift its rotation slightly, or tilt its axis. This could change the length of Martian days, or the patterns of its seasons. Smaller impacts spread over millions of years could wear down the stability of its orbit, creating long-term wobbles. Venus, already rotating slowly and strangely compared to other planets, could see its spin further disrupted. The pressure of repeated impacts might even change the direction of its rotation. Jupiter, being so large, would not have its orbit shifted much, but its many moons could be affected. Fragments pulled into its system might collide with moons like Europa, Ganymede, or Io, leaving craters and altering their surfaces. The potential for fragments to cause chain reactions is high. A piece striking Mars could eject even more debris into space, sending smaller fragments into new orbits. Some of these might cross back toward Earth's orbit or head out toward the asteroid belt. Venus could produce the same effect, scattering secondary debris after major strikes. In this way, the destruction of one planet could lead to a cascade of impacts across the inner solar system. Each planet hit would not only suffer damage, but also contribute to spreading the chaos further. Over time, the solar system could take on a new shape. The asteroid belt might grow larger, fed by fragments that never found stable orbits. Mars and Venus might gain new moons, formed from debris that settled into orbit instead of crashing to the surface. Jupiter's powerful pull might gather enough fragments to form temporary rings, glowing bands of rock and dust around the giant planet. These features could last millions of years, slowly dispersing as gravity and collisions reshape them again. The history of our solar system suggests that such events are not far-fetched. Craters on Mars and Venus show evidence of massive impacts in the past. Jupiter's atmosphere still carries the scars of objects that struck it within our own lifetimes. Even Earth bears the memory of the impact that created the Moon, a collision so powerful it must have scattered fragments across nearby space. Those fragments may well have struck Mars, Venus, or even Jupiter in the distant past, influencing their evolution. What we see today, the landscapes of Mars, the harsh climate of Venus, the storms of Jupiter, may already carry the marks of impacts from other worlds. From the perspective of time, these changes happen both instantly and slowly. The moment of impact is sudden, with energy released in seconds. Craters form, atmospheres heat, and debris flies outward. But the long-term effects unfold over millions of years. Orbits shift gradually. Moons form from slow accretion. Atmospheres thin or thicken step by step. What begins as a violent moment becomes a slow rewriting of planetary histories. The solar system is never static. It evolves through impacts. And the shattering of one planet could set off a chain of changes that last for ages. To imagine this visually, think of a cue ball striking a cluster of billiard balls. The first strike scatters the balls in all directions. Some stop quickly, others roll far, and some collide again, scattering further. In the solar system, the shattered fragments are the billiard balls, moving not on a table but through space. Each collision changes the pattern, and the game continues for millions of years. Mars, Venus, and Jupiter are targets on that table, each one shaped by the pieces that reach them. The destruction of a planet is not a private event. It spills across space, involving every neighbor in the system. Fragments from the catastrophe travel far and carry the power to alter the fate of other worlds. Mars may grow colder and more barren, Venus more violent, and Jupiter more scarred. The solar system itself becomes a record of the event, with every planet touched in some way by the fragments of the shattered world. When a planet shatters, its fragments scatter in every direction. Some remain nearby, orbiting as rubble. Others drift outward, pulled into longer paths around the Sunday. Over long stretches of time, gravity decides their fates. Jupiter may capture some, Mars and Venus may absorb others, but many will continue circling until their orbits bring them close to the Sunday itself. For these pieces, the journey ends not with a quiet drift into darkness, but with a violent plunge into the heart of the solar system. Large fragments falling into the Sunday would not change its overall balance. It is far too massive for that, but they could create localized disturbances, bursts of activity that echo across space. The Sunday already consumes material from time to time. Comets, drawn in by gravity, streak across the sky and burn up in its outer layers. These are small compared to planetary fragments, yet even they can produce visible flashes as they disintegrate. Now imagine an object far larger, a mountain-sized or even continent-sized piece of shattered planet spiraling inward. As it approaches, the Sunday's heat strips away gases and melts rock. The fragment becomes a glowing ball, leaving a trail of vaporized material behind it. By the time it reaches the surface, it is no longer a solid body, but a cloud of plasma mixing with the Sunday's outer layers. The collision releases energy, creating a localized shock that disturbs the solar atmosphere. These disturbances can take several forms. The impact of fresh material triggers turbulence in the Sunday's outer layer, known as the photosphere. This turbulence can lead to sudden brightenings, much like solar flares, as magnetic fields respond to the injection of energy. The corona, the Sunday's outer atmosphere, may react with bursts of charged particles, sending solar wind racing outward at higher speeds. From Earth or any nearby planet, the effect would appear as a sudden surge of radiation and solar activity. Satellites, power grids, and communication systems, if they still existed, would feel the consequences. The scale of the disturbance depends on the size of the fragment. A small piece might vanish with barely a ripple, like a pebble tossed into a lake, but a fragment dozens of kilometers wide could unleash an outburst comparable to or larger than the most powerful solar storms. The Sunday produces energy on a scale we can barely comprehend, but it is also sensitive to disruptions in its outer layers. The addition of dense rocky material does not go unnoticed. It spreads shockwaves through the plasma, and those shockwaves can trigger chain reactions in the Sunday's magnetic fields. The process can be compared to dropping a heavy stone into a pot of boiling water. The water is already in motion, bubbling and steaming. When the stone hits, it sends new waves through the boiling surface, making the pot surge and spill over. The Sunday is the boiling pot, seething with plasma and energy. A falling planetary fragment is the stone. The disturbance may not last long compared to the Sunday's lifetime, but for nearby planets, it is violent and immediate. Astronomers have observed smaller versions of this. They have seen comets plunge into the Sunday, vanishing in bursts of light and heat. Some of these plunges are powerful enough to trigger coronal mass ejections, where huge amounts of solar plasma are thrown into space. If fragments of a shattered Earth-sized planet fell into the Sunday, the effect would be magnified many times over. Entire regions of the solar atmosphere could be destabilized, producing storms that stretch across the Sunday's surface and hurling radiation outward in all directions. For planets like Earth, if it still existed nearby, these outbursts would be devastating. A strong coronal mass ejection can already disrupt technology, cause blackouts, and expose astronauts to harmful radiation. Multiply that effect by the energy of a planetary fragment colliding with the Sunday, and the consequences would reach far beyond technical failures. Radiation storms could strip atmospheres, boil away water, and sterilize surfaces. Mars and Venus would also feel the impact. Their thin or thick atmospheres alike, bombarded by streams of charged particles. Even the outer planets could see changes in their magnetospheres. As the solar wind intensified, over time, repeated infalls of fragments could reshape the Sunday's rhythm. The Sunday goes through cycles of activity, with sunspots and flares peaking every 11 years. Injecting massive amounts of material into its outer layers could disrupt this cycle, creating irregular bursts instead of steady peaks. The Sunday might flare unpredictably, releasing energy in fits and starts. From a distance, it would seem restless, flashing with sudden surges that mark the arrival of new fragments. The path of fragments into the Sunday would not always be straightforward. Some would spiral inward slowly, dragged by gravitational interactions over millions of years. Others might be sent on direct courses after close encounters with Jupiter or other large bodies. Once a fragment crosses a certain distance, the Sunday's pull becomes irresistible. It accelerates to tremendous speeds, reaching hundreds of kilometers per second before impact. The kinetic energy it carries is enormous, and when that energy is absorbed by the Sunday, it produces a shock that radiates outward. Think of a meteor entering Earth's atmosphere. A small pebble burns up with little notice, but a large rock can create a fireball brighter than the Sunday. The same principle applies on a larger scale when fragments hit the Sunday. Most disappear quietly, but the largest become cosmic fireballs, releasing bursts of energy that ripple across the solar system. These bursts are not enough to harm the Sunday itself. It is far too massive, but they are powerful enough to endanger any planet caught nearby. In the long view, the Sunday consumes material constantly. Dust, comets, and asteroids fall into it every year. But planetary fragments would be different in both size and frequency. After a world is shattered, debris could feed into the Sunday for millions of years. Each impact would be a reminder of the original catastrophe, keeping the solar system unsettled long after the initial event. The Sunday, normally a steady source of light and warmth, would show violent outbursts whenever a large fragment crossed its path. For observers elsewhere in the galaxy, the effect could be visible. Stars sometimes show unusual flares or bursts of brightness. Astronomers debate whether these events are natural fluctuations or the result of material falling in. A shattered planet in orbit around a distant star could explain some of these mysteries. To a telescope far away, our own Sunday would appear the same if it consumed fragments from a destroyed Earth, flashing unpredictably as the material triggered storms in its atmosphere. In this way, the Sunday is both the end and the amplifier of a planetary disaster. The fragments that fall into it vanish, but not quietly. They create disturbances that radiate outward, changing the conditions of the entire solar system. What began as a violent collision on one planet spreads across space, until even the Sunday itself carries the marks of the destruction. The star remains, unchanged at its core, but on its surface and in its storms, the evidence of shattered worlds becomes impossible to miss. When two planets collide, the violence of the event does not stay hidden within their system. The light and energy released can shine across immense distances, turning a single moment into a spectacle visible to distant observers. From Earth, we look out into the night sky and sometimes see the traces of supernovae, gamma ray bursts, or collisions between stars. In the same way, if a planetary impact occurred in another star system, its explosion of light and heat could be seen across galaxies. To anyone watching from afar, it would look like a sudden star igniting, flaring for days or weeks before fading back into silence. The source of this brilliance lies in the release of kinetic energy. A planet-sized body traveling at tens of kilometers per second carries unimaginable momentum. When it strikes another world, that energy converts instantly into heat, light, and radiation. The result is an explosion bright enough to rival the host star, at least for a short time. The surfaces of both worlds melt and vaporize, glowing like miniature suns. Clouds of debris scatter outward, reflecting light in every direction. For astronomers with telescopes in another galaxy, the event would stand out as a new point of brilliance, flaring and then slowly fading. To picture the scale, consider how much energy a nuclear detonation releases. Now multiply that by billions and then multiply again by millions. The glow from such an event would not be a narrow flash like lightning, but a sustained burst of radiance. Days or weeks might pass before the light dimmed enough to blend back into the surrounding star field. To a distant civilization, It would look like the sudden birth of a nova, a star flaring to life. Only close study would reveal that the light came not from a star but from planets colliding in catastrophic fashion. Dust and gas thrown into space would add to the spectacle. As debris spreads outward, it would form a glowing shell around the site of impact. Sunlight or starlight shining through the material would scatter, producing colourful halos. To an astronomer with the right instruments, the cloud might show traces of elements like silicon, iron, and magnesium, materials common in planetary crusts. The signature would be different from that of a dying star, marking the event as something distinct. It would tell a story not of stellar collapse, but of planetary destruction. Over longer periods, the debris would remain visible as well. Just as supernovae leave behind expanding remnants that glow for centuries, a planetary collision would create a disk of dust and rock that could be seen for thousands of years. Telescopes might record it as a ring or halo around the star, a reminder of the event long after the initial flash faded. Within that debris, new bodies might form, eventually creating moons, asteroids, or even a new planet. For distant observers, the spectacle would not end with the explosion, but continue as a slow evolution of the system's structure. From the ground of a nearby world, the sight would be overwhelming. Imagine looking up at the night sky and seeing two planets collide. First, a bright flash, then a sustained glow brighter than the full moon, filling the heavens for days. Dust clouds would spread across the sky, lit from within by molten fragments. For anyone capable of seeing it, the event would be burned into memory as a night where the sky itself turned to fire. For distant galaxies, the same event would appear as a new point of light, a tiny spark in the vast darkness, but still visible across unimaginable distances. History provides hints that astronomers may already have seen such spectacles. Infrared telescopes have recorded sudden brightening around young stars, where dust and debris glow after impacts. Some exoplanet systems show evidence of giant collisions, their light curves changing suddenly as dust blocks starlight. These observations suggest that collisions are not rare. They are part of the normal life of planetary systems. What we call a spectacle is also a stage in cosmic evolution, one that shapes worlds and leaves glowing evidence for others to see. The visibility of a collision depends on the size of the bodies involved. Small asteroids striking planets would not shine across galaxies, but when entire worlds collide, objects the size of Earth, Mars, or larger, the energy release becomes bright enough to stand out even across the distances between stars. In that sense, the universe acts like a theatre, where some events are quiet, hidden from view, while others are so brilliant that they draw attention no matter how far away the observer may be. Think about the way fireworks look in the night sky. A single sparkler glows faintly, visible only up close. But a massive firework launched high into the air bursts into light that can be seen for miles. A planetary collision is the cosmic equivalent of the largest firework imaginable. Its light may cross interstellar space, traveling millions of years before reaching the eyes of a distant observer. By the time it arrives, the event itself has long ended, yet the spectacle lives on as a bright memory carried by light. The duration of brightness matters as well. Supernovae fade slowly, remaining visible for months. Planetary collisions fade faster, but they still last long enough to be noticed. An astronomer tracking stars night after night would see the sudden flare and be able to measure its decline. The data would reveal the speed of the debris cloud, the energy of the impact, and even the composition of the shattered worlds. To distant scientists, the spectacle would not just be a light show. It would be a source of knowledge about how planets form, evolve, and sometimes die. Closer to home, the collision that may have formed Earth's moon would have been such a spectacle. If a distant civilization had looked our way 4.5 billion years ago, they might have seen a sudden burst of light near our young Sunday. They would have recorded it as an extraordinary flare without knowing it marked the birth of the only natural satellite Earth has ever had. To us, the moon is familiar, but to them, it might have been seen as the aftermath of a glowing explosion. The idea that collisions create visible spectacles also connects to how galaxies themselves evolve. In some systems, astronomers see excess infrared light, thought to come from dust produced in planetary smash-ups. Others show strange gaps or rings in debris disks, evidence of impact scattering material. Each one of these observations is a kind of cosmic firework, a visible sign of the violent processes shaping worlds. To distant observers, these spectacles are rare events worth watching, much as we watch supernovae and other stellar outbursts today. A planetary collision is destruction for those involved, but from afar, it is beauty. It shines as a point of light cutting across the darkness, a brilliant explosion visible across galaxies. The fragments may scatter, the debris may cool, but the flash endures in the memory of the universe, carried as light to every corner that can see it. To distant observers, the event is both a warning and a wonder, showing how fragile planets are and how brightly they can shine when their stories end in fire.